Hello, welcome to a Witekio and Avnet webinar on securing IoT systems end to end. So this is a really expansive topic. We're going to do a good overview today, but I don't think we can realistically cover all aspects of security for all manner of IoT systems. So I think consider this a primer rather than an encyclopedia. The plan today, we're going to have three 45-minute sessions, each on a different topic, looking at different aspects of security within the IoT ecosystem. Each of those 45-minute sessions will start with a presentation from one of the engineers we have on the call with us today. And then we'll dive into a Q&A session, ideally relating to topics that have just been raised. So I'd ask that if you have any questions that arise during the talk itself, feel free to raise those in the chat, and we'll then ask those and run through those in the Q&A session immediately after the talk. This is designed to be a collaborative event, so we really want some good questions. So please don't hesitate to pop a question in the chat, and we'll be happy to run through those after each of the talks. So the talks in question, Nicholas Beck is going to start us off with a look at security standards in the IoT space. This is sort of a somewhat nascent area, so there's a lot of new standards being introduced, and a lot of variance between those standards worldwide. So Nick's going to give us an overview of that side of things, and going to a discussion following that. Ed's going to look at security by design. So that's looking at how can we bake security in from the outset of a new product development, rather than, as we sometimes see, it being considered somewhat as an afterthought, and generally it is much more expensive to do it in that manner. So considering and designing security in from the outset can be a real benefit, and Ed will talk us through some of the sort of best practices, potential pitfalls associated with that. And then James is going to take a look at IoT systems end to end, and how you go about securing that from hardware through to the cloud, and what level and what kind of testing and strategies you might need to apply in such a system. So without further ado, I would like to hand over to our first speaker, Nicholas Beck, who's going to take us through IoT security standards. Over to you, Nick.
Hi, everybody. So today I'm going to be talking about some IoT security standards and frameworks. So what do we mean by security? Let's start with a few definitions. Security is a noun meaning protection from threats. And narrowing that down to our domain, according to Nist, cybersecurity is the ability to protect or defend the use of cyberspace from cyber attacks. And information security is the protection of information and information systems from unauthorized access, use, disclosure, disruption, modification, or destruction in order to provide confidentiality, integrity, and availability. So in short, cybersecurity is related to protection from attack on the internet, whereas the scope of information security is broader and is related to protection of any asset from any attack. The main properties of security, also known as the Holy Trinity, are confidentiality, where only the authorized agents can access some data; integrity, some data cannot be tampered with by an authorized agent; and availability, so the access to some resource must be guaranteed. But also authenticity, So some agent must prove its identity through the use of a secret she is assumed to be the only one to know. Traceability. Some accesses and access attempts are traced, and the traces are stored and usable. And non-repudiation. Some agent cannot dispute some actions she did on the system. Sorry, I seem to have lost my slide deck a second. So, IoT security is not absolute and can never be guaranteed. It's a journey rather than a destination. New vulnerabilities are constantly being discovered, which means there's a need to monitor, maintain, and review both policy and practice on a regular basis. So why do we need security? Not having a secure IoT system is a risk to not only users, but also to your business, who could be held liable. Some of the primary things you should be concerned about are user data exposure. Many IoT devices collect and distribute personal information. Fitness trackers, heart rate monitors, sleep trackers, and surveillance devices all send out information that could be misused. Business data exposure. So IoT devices, when linked to a company's network, can open security holes and can expose the business to a higher level of vulnerability or data loss. Many IoT devices contain actuators, which, if activated incorrectly, could cause physical harm to your customers. Things like ovens and coffee makers have heating elements that could trigger a fire, or connected vehicles could be turned off in the middle of a journey or have their brakes disabled by a third party, for instance. With respect to service failure and downtime, in the event that there is some IoT service failure, some devices can pose fatal threats. For this reason, connected medical devices need to still function properly when offline, for example. And any lack of availability is likely to have an impact on business reputation, revenue, or both. So, as previously mentioned, IoT hacks can result not only in liability for data loss and identity theft, but also potentially life or property liability as well. And companies manufacturing connected devices are becoming more responsible than ever for this. Other effects, other reasons why we need to consider security are that a security defect or breach can result in reputation and brand damage, that some geographic regions, product markets, and verticals have legislation that must be complied with in order to be able to access those markets, and that security is a product differentiator. So a trusted product with superior security will have a competitive advantage over its competitors. To illustrate the prevalence of IoT devices as a target, some Kaspersky research shows that there were 1.5 billion attacks against IoT products in the first 6 months of 2021, and that represented a 100% increase on the same period in 2020. So Ed will discuss this more as part of the secure development lifecycle, but I just want to say that the secure requirements must be defined at the start of the project. And if you're listening to this now thinking that your in-progress project is doomed, then don't panic. All's not lost, but it will almost inevitably be more expensive, time-consuming, and maybe not possible to secure the product sufficiently, depending on what your exact product security requirements are. You'll also want to identify what IoT security guidelines and requirements that you need to follow, including any legislation in specific geographic regions and any requirements for particular sectors or verticals as well. And lastly, you should be aware that use of a secure development process is an expected practice in all of the IoT security frameworks and standards. So, when IoT devices started being produced, there were no adopted IoT security standards, and the products were mostly shipped with little or no security. So attacks on and from IoT devices have become commonplace in recent years. For instance, large-scale distributed denial of service attacks from compromised IoT devices acting as a botnet. There's many examples, but I won't dig into those now. This fact prompted many different standards bodies, governments, and organizations to develop and publish guidelines to build secure IoT devices and services. But these activities took place in parallel. So the result is that we've got hundreds of different standards, frameworks, guidelines, and technical documents around IoT security. And a recent survey by PSA found 48% of decision makers rate the lack of unified standard as one of the greatest problems to IoT security. This diagram shows the mapping of external references from ETSI EN 303645. And you can see there are a large number of sources of security information published, and that there's a lot of mappings that occur between them. For instance, Enisa noticed that 70% of IoT security issues are common to all sectors, and thankfully, these various organizations developing these guidance and standards have been open and collaborative with other groups. So while there's a huge number of publications, there's also a lot of commonality between them. So for example, this shows a mapping of EN 303645 provision 5.1, which is no universal default passwords. And it shows a mapping to an array of other standards and frameworks from governments and industry bodies and standards organizations. And you can see there's like a kind of a clear one-to-one mapping between a lot of these. And this is a similar picture seen for all 13 provisions of EN 303645. So the standards and guidelines state what should be done and the best practices for securing IoT devices. And there are a couple kind of major ones, plus a number of others as well. So ETSI EN 303645 is a European standard that's being adopted internationally across many parts of the globe. It was originally based on work by the UK government Department of Digital Culture, Media and Sport that they published in 2018, but was later adopted by ETSI as a technical specification under TS 103701 and TS 103645, and then later promoted to a European norm, so to a standard. And it contains the baseline requirements for IoT consumer device security. It's published in 2020. Related to this is ETSI TS 103701, which is a technical specification for assessment for consumer IoT. And it says how to certify and check compliance of EN 303645 for a product. It's intended to support the EU cybersecurity certification scheme, and it was published in 2021. There's also ETSI TR 103621, which is an implementation guide, which is currently in draft, and that's due for publication in Q2 of this year. So that will contain a number of examples of how to implement the recommendations and requirements that exist in 303645. Across the other side of the Atlantic, the Nist 8259 series of reports provides guidance for manufacturers of IoT devices, and the series consists of Nist 8259, which contains foundational guidance and recommendations for IoT device manufacturers, 8259A, which contains specific technical capabilities that manufacturers should consider and implement, and 8259B, which contains specific non-technical capabilities that manufacturers should consider as well. There's also NIST 8228. This aims to educate management on why IoT security and privacy risk differ to other IT devices, but is probably of minimal value to teams who are actually designing and implementing a secure IoT product. So there are also many other guidelines from organizations like ANSI, GSMA, Enisa, the DCMS, ISO. We'll continue to focus on 303645. It supports a good baseline for connected consumer products, provisioning a set of 13 recommendations, where the top 3 are no default passwords, implementing a vulnerability disclosure policy, and keeping software updated. There are also specific data protection provisions for consumer IoT devices, and it provides a useful security baseline that spans a variety of consumer IoT devices. But sometimes there'll be additional sector-specific requirements that need to be implemented also. So if we're going to use EN 303645, we're going to implement that. What are the steps that we need to take? Essentially, there are 4 steps. The first is to review the concepts on device architectures, network architectures, and device states in the standard itself and some of the annexes included in it. Step 2 is to implement those provisions. So the device manufacturer must implement all 33 requirements, and they should implement all 35 recommendations as well. The device manufacturer also needs to record the rationale and justification for if a recommendation is not implemented. The third step is to complete an implementation conformance form. And the fourth and final step is to prepare for assessment. So that can be either in-house or external by a third party. And that's using the assessment specification, so TS 103701. So there are third-party test labs like UL who have some proprietary labels that are based on TS 103645 and TS 103701 that you can use those labels in kind of marketing material and the likes. The 13 provisions of the standard itself are no universal default passwords, implement a means to manage reports of vulnerabilities, keep software updated, securely store sensitive security parameters, communicate securely, minimize exposed attack surfaces, ensure software integrity, ensure that personal data is secure, make systems resilient to outages, examine system telemetry data, make it easy for users to delete user data, make installation and maintenance of devices easy, and to validate input data. And as we mentioned before, there's also some data protection provisions. But so I won't go into much to do with personal identifiable information in this talk, but there's another raft of standards and things that exist around that. So looking at the Nist 8259 and across in the USA predominantly, it provides simple and applicable security guidance to IoT users and manufacturers, and it's being proposed for ISO standardization. There's a lot of commonality between EN 303645 and other references with Nist 8259, and it contains a clear mapping to those other IoT security references within the document, which is very useful. There are less criteria in the Nist 8259 than there are in EN 303645. So it contains 10 capabilities, which are equivalent to the provisions. There's device identification, device configuration, data protection, logical access to interfaces, software update, cybersecurity state awareness, documentation, information and query reception, information dissemination, and education and awareness. So the two which kind of, from a technical side of things, which differ from EN 303645 are cybersecurity state awareness. So this refers to the device monitoring and logging cybersecurity events that occur on it and making those logs available, accessible, but only to authorized entities. And device configuration refers to being able to change the device's software and firmware configuration, and that such changes can only be performed by authorized entities as well. So frameworks typically provide more specific security requirements to be met than the standards. And these will have some kind of label, typically have some sort of label or badge or mark or certification that can be used in product marketing and the likes. The frameworks often map the guidance from multiple guidelines and standards. So typically this will be EN 303645 and Nist 8259. And some example frameworks include the IoT Security Foundation's Security Assurance Framework, This is a checklist with roughly 200 requirements. It maps both EN 303645 and Nist 8259. It has a number of assurance levels, 5 in fact, to meet different security objectives. And it can be, depending on what assurance level that you're trying to attain, then it could be you can perform a self-completed assessment through to like a full third-party audit by a test lab for the higher assurance levels. Once all the criteria have been met in the assessment, the device manufacturer can use the IoTSF badge label in marketing material. PSA certified IoT security framework is basically contains an ecosystem of OEMs, system software providers, so kind of operating systems, real-time operating systems and the like, and semi-vendors who have certified products, and they've basically taken their part of the system and certified it through the framework, and then it's possible to leverage those certifications by like an OEM, so that they can, if they take a SOC which has already been certified and system software that's already been certified, then they only need to get their own kind of application level certified. So there's a number of different security certification levels. A lot of the focus is on silicon root of trust for those higher levels. And that involves a third-party assessment by a test laboratory. And again, it also maps EN 303645 and Nist 8259. Some other examples of frameworks are the Industrial Internet of Things Security Framework, the Cloud Security Alliance IoT Security Controls Framework, and the OWASP Internet of Things Security Verification Standard. Just for a quick comparison, OWASP ISVS is a community effort to establish an open standard of security requirements for IoT applications. And like the IoTSF Security Assurance Framework, it has multiple protection levels based on the security objectives. And similarly to the IoTSF framework, in comparison to the IoTSF framework, the OWASP ISVS is a bit less specific, but they cover a lot of the same ground. So this also uses a checklist approach, and that works well in terms of performing a security review and checking coverage. It's a good pragmatic tool, but because it's quite generic, it has a couple of drawbacks. So some of the requirements are quite high level, and you need to be worked on if one wants to end up with a usable and relevant checkpoint. And the other point it has is that the approach doesn't really take into account the specific security problem for a given product. So no security architecture description is promoted, and no rationale regarding the critical aspects of the product and the way they are to be protected is required either. So moving on to kind of regulation and legislation, we're starting to see that regulations are being mandated in countries across the globe. It often trails behind the state of the art and the use of full best practices, but is a starting point. So examples include the EU Cybersecurity Act, which will allow for certification which is recognized across all EU member states, and EN 303645 and the assessment spec TS 103701 will be well placed to provide the foundation for basic level IoT assurance. The EU Cybersecurity Act isn't actually yet enforced for IoT devices, but it's coming in the future. And then in the USA, there is also the Radio Equipment Directive in the EU as well, but that is in force, but that affects a subset of products. So that covers things like childcare radio equipment, toys, wearable devices, and a couple other things. Then in the USA, at a federal level, there's IoT Cybersecurity Improvement Act of 2020, This only applies to devices which are purchased or controlled by federal agencies, but that's likely to kind of trickle down into like consumer purchased items as well. And then there's also the Cyber Shield Act, which was reintroduced in March 2021, and that aims to regulate consumer IoT products directly with a labeling program that sets different benchmarks for different assurance levels. Then at a state level, California and Oregon have already passed some state laws relating to cybersecurity of IoT devices, and there's a number of others which are following suit as well. These are quite basic at the moment. They mandate reasonable security, where that's quite loosely defined, and that the product has a unique password or a user-defined authentication mechanism. And then in the UK, the Product Security and Telecommunications Bill recently went before Parliament, and it mandates 3 requirements: no default passwords, that a vulnerability reporting mechanism exists, and that a clearly defined period for security updates is published. So as you can see, this kind of correlates with the top 3 of EN 303645. This image shows countries across the world with IoT cybersecurity regulations. It also shows those which can be addressed by complying with 303645. So outside of the EU and the Cybersecurity Act, there are the following that build on EN 303645. We've got Finland's National Consumer IoT Certification Scheme. We've got Singapore's National Cybersecurity Labeling Scheme. There's Vietnam's list of baseline cybersecurity requirements for consumer IoT. Australia's Code of Practice. India's Code of Practice for consumer IoT. And the UK's PTSI. But of all of these, only the UK and the EU Radio Equipment Directive are currently mandatory. The rest are enforced but voluntary. And as I mentioned before, the EU Cybersecurity Act will come into force, will be mandatory at some point as well for IoT devices. Then looking at other countries with regulation, Brazil, Canada, Saudi Arabia, UAE, and the USA have some mandatory regulation already in place. And countries like China and Thailand have regulation that's currently work in progress. So external assessment and certification enables trust and confidence. It allows you to hold a competitive edge, ensuring compliance and gaining access to certain markets. This slide from the PSA Certified 2021 Security Report paints a clear picture of the drivers for certification, and that its importance is largely agreed upon across the industry. So to give some examples, there are a number of labs that have schemes and products based on EN 303645, and those include UL's IoT Security Rating Assessment, TUV Sud and TUV Rhineland offer testing against 303645. The global platform CESIP has been mapped to EN 303645 and TS 103701, and there's many others as well. So just to wrap up on this section of the presentation, some key points are that IoT security is a constantly evolving landscape, that regulation is increasing, that being able to provide evidence of security capability is also increasing, that global defragmentation of standards and frameworks is starting to happen, particularly for baseline security requirements. And there's a lot of commonality between them all, as they're all following best practices. That you should identify specific requirements for your particular regions and market sectors prior to starting your project ideally. And I've also provided some useful IoT security mapping links. Thank you for your attention. We'll now take any questions.
Thank you for that, Nick. think we've had a few questions in the chat. First one was from Rune Torbenson. Thank you, Rune. Probably one for you, Nick, I think. When is a standard a guideline and when is it a requirement?
Good question. There seems to be like there's kind of a bit of a fuzzy line between these. So a standard. So these basically, let's take an example. EN 303645 is now a standard, but it started off as a set of guidelines, which was then kind of converted into a technical specification before it kind of went through some formalities and normalization into a standard. So I guess the question maybe is, do I need to follow guidelines or do I need to follow standards? And that is going to be very much dependent on where you're aiming to sell your product and what type of product it is.
Yeah, so we see a lot of that being driven by the market that product's being sold into. If it's a hard requirement, often it will be dictated by the marketplace that end customer is looking to target.
Yeah, I mean that's my view. If a standard is mandated by the market, then it's a requirement, but otherwise it's a guideline.
I think it's a good summary. Agreed. Some more great questions from Rune in the chat as well that I will come back to, but there's one coming from Martin Duffy that I think is a great question. Thank you, Martin. How applicable do you think the legislation will be to non-consumer IoT products? For example, IoT products in a smart building or in the manufacturing environment? Nick, I know you were working on an active project that targets one of those markets. Any thoughts on that?
I think that there'll be a lot of crossover between it all. I think that given all of these things are sharing the same best practices and the commonality that exists between them all, and the commonality that exists in the problems that are trying to be solved. So that the attack vectors and the vulnerabilities and everything are largely shared across all domains. So I think that this will end up making its way. This legislation will make its way across to the industrial space and the smart building space as well. Maybe a bit slowly, but I think just adoption by industry generally of these better practices will make it more commonplace as well.
Absolutely, and certainly the project that I mentioned there, security is the project that's targeting smart buildings in that sort of IoT setting, and security is pretty much the most fundamental concern for that end customer, for their market. So that really matters. That's a real concern for their customers and therefore a real priority for them in their development. So while the market in that instance hasn't got fixed standard that they have to comply with, that customer has been proactive about identifying a framework that is very nascent, but is starting to certify organizations, and they've been proactive in engaging with that certification body to gain these standards so that they can be more trusted within the marketplace and gain a competitive advantage over their competition. So it's not just necessary for keeping data secure and platform secure. It's already being seen as a means of gaining a competitive advantage, and rightly so. Ed, James, anything to add on that one?
James, you're on mute.
Nothing much
on.
really. I think for in terms of industry, if there are ISO requirements for that industry, they may have to find conformance systems. But I think really we're coming down to the mandatory requirements of legislation as opposed to the market availability. If people can buy stuff cheaper without it conforming, then unless it has to, it probably won't.
I was going to say, I think that
Yeah, I mean, certainly.
Yeah.
Oh, I was just going to say my expectation in the future, as kind of the landscape of standards sort of settles, I'd expect non-consumer markets to be the real driver of the uptake of these standards, because if you look at like the construction industry, that's historically always had much more regulation than, say, you know, consumer electronics. So if you're going to build electronics into a building, and you know it's going to be physically, you know, cemented into the walls, you know, I'd expect that in time to come under some kind of building regulations. So you expect to see some sort of security standard tie-in to that. We'll see what the future holds, I expect.
It's certainly going to be an evolving landscape.
Yeah, I think that there's nothing in the legislation for consumer products which isn't going to translate into non-consumer products. And I think that on top of that, the legislation is something which has really helped drive this home. So people have been aware of a lot of the other risks and the reasons why you want security for a long while. But as others have just said, if there's kind of being able to provide cheaper products, there's always going to be people who are going to buy the cheapest thing that's possible. So without that legislation in place, that's what helps kind of gate and guard that.
Thanks, Nick. Question from Bernard Vikens in the chat. Do you confirm that the market will require secure elements in IoT consumer applications? I know we've got some experience with that. Any thoughts on that? Anyone want to take that one?
I don't think that
to kick off, but
Go on, Ed.
Sorry. I was going to say, I think anyone who's making a device, any company that makes a device that doesn't want to see unapproved code running on it, is going to need a secure element of some sort. But the thing to bear in mind is a lot of system on chips now sort of come with everything you need for secure boot and secure key storage sort of built into the chip. So if you mean a separate secure element, possibly not for a device that's got something more advanced than a you know, an 8-bit microcontroller. If it's got something closer to you know, an applications processor with multiple cores and separate co-processors and so on. The ones that we see coming to market in the last decade have all got kind of secure boot built in, and yeah, red and black key blobs.
Thanks, Ed. I think I've got a few thoughts to add on to that. I think it depends what you're looking to achieve with that secure element. So as Ed says, one of the common uses there, with whether it's TPM, secure elements, or that functionality built into the system on chips, is that secure boot, you know, validating that only approved software will run, and that's a very important use case, but it's not the only one. And so we also see that same hardware-based root of trust used to secure communications between devices, especially within an IoT system. Some implementations allow you to do that quite easily. Others intentionally restrict higher level software from reading those keys out. So there is some scenarios where you might want both sort of secure boot within a SOC and a separate secure element or TPM, depending on what you're looking to achieve. So it's really, I think, a case of working out what you want to secure with that, what the use cases are, what your system on chip can already support from its secure encoded hardware, and then based on that, whether you need any other hardware to complete sort of the security of that platform. There's a great question from Rune in the chat, which is so I just lost it. Who is responsible for security, especially if a product has a number of sub-suppliers? I think we'll probably learn a bit more about that in Ed's talk in a minute, but I think the flippant answer from my point of view is everyone. And that's one of the key bits of certainly the SDL is making everyone aware of security, what the requirements are, and what's needed as part of that project to meet those requirements. And that's true whether or not suppliers in subcomponents are involved. How that works in practice, Titus has done a great summary in the chat there as well. In practice, it will be the product owner, the integrating company who coordinates that, but they can't succeed in that space alone. They will need the suppliers to be aware of those requirements and to comply with those throughout. Ed, anything to add on that?
Yeah, I mean, in a wider scope, this is a question I think that the whole IT market in general has to face in time. I remember going to a trade show a few years ago. It was just a general IT trade show, and people were talking about breach insurance. So if you get breached and doxed or whatever, you get insurance to cover the cost of recovering from that. And I said to someone on the stand, who pays for this? And he's like, well, whoever is prepared to pay for it and wants to bear the cost of getting breached. I said, well, if the breach happens through a router that you buy and put in your network, shouldn't they pay for it? So I think when it comes to who's responsible for insurance for security, I think it's a case of who wants to take responsibility is the pragmatic answer. Who's going to suffer the most from the lack of security? That's the person who really needs to bear down on their suppliers and say, I demand better from you. In a making a device, an IoT device sense, but also in a running a corporate network sense. If you're buying a router, that's where a lot of people get in if they're serious about it. And if it turns out the breach was through a certain brand of router, you need to demand more from the company that makes that. How that actually shakes down, whether it's court cases, litigation after the facts, or demanding conformance to a standard up front, again, it's sort of early days, really. That's a vague answer, sorry.
Thanks, Ed. Had this question in the chat on sort of a logistics question from Risto Sutinen. Will the slides be available for download after this event? Just been having a quick chat with the marketing team. Yes, we will make those available, but it won't be through the Livestorm website that you're using today. We will collate the slides together and make them available through the Witekio website and communicate that to the registration to the registrants of this meeting. So keep an eye out for an email after the workshop with a link. Lovely. Looking at timing, we are on the dot for moving on to our next speaker. If you've got any questions on the certification side of things, do feel free to keep adding them to the chat. Happy to pick up some of those in the next Q&A. I think there'll be, as you'll see, there is some overlap between each of the topics we're going to talk today, so don't feel like your window for asking questions about certifications is closed. Just stick them in the chat. So without further ado, over to Ed, who is going to take us through security by design.
Oh, come on, really?
It's having some bandwidth problems.
I just had a momentary bandwidth scare. Okay. Okay. Thank you, Phil. Yes, welcome to my session on security by design. So what I'm going to be covering in this is firstly the most obvious question of what is security by design, what does that mean, and then I'll go through how that translates to actual activities that that are required when developing software, focused mostly on developing embedded software for IoT devices. And then I'll conclude by answering upfront some common concerns that are often expressed when you talk about this stuff. So let's get an idea of what it is we're talking about in this session. What is security by design? Also often referred to as secure by design. I think the terms are interchangeable. So the way I look at it is defined as a concept. The concept that you can't just add security after the fact or at the end of a development. You don't get to a stage in the development where you go, okay, now we're going to do the security part. The security has to be included throughout all of the stages of a project. So what does that actually mean in terms of doing something? Well, if you look at the different organizations online that mention secure by design, or articles on blogs and books, etc., what the term implies that you should actually do can refer to one of two things. So for some people, it's a set of guiding design principles that you then see in the end results of your development. So in effect, a sort of a set of design principles or tenets of security within the design. But the main definition, the one I'm going to focus on here, when you talk about secure by design, means ensuring that the process used to create the end results, i.e. the software embedded in a device, ensuring that the process to create that is set up to ensure that the end result is secure. So the development process by design ensures a secure result. And that, when you look at it in that definition, that quickly leads on to a discussion of development practices that you need to include in your development life cycle to ensure that vulnerabilities don't creep through into the final results. So it's these additional activities during the development process which by design ensure that the end result is secure. So a few words on what security by design isn't. It's not a specific product, book, or process from a particular vendor, say. Some security standards do mandate use of, one variation or another of the practices that I'll be describing shortly. However, it's really better to figure out what you need to be doing independently of any particular standard. You should sort of figure this out up front and kind of get those practices ingrained into the habits and the working culture of your team, rather than just and then later when you come to sort of trying to certify to a standard, as Nick has described, filling in any gaps, and if you follow all the practices that I'm about to show you, there probably won't be any gaps. All you have to do is sort of translate the terminology into what they use in the standard to sort of achieve the requirements of that standard. Now there are, so what I'm going to do is describe the practices that you need to follow in very general terms, agnostic of any particular framework. Okay, because it's unlikely that you'll go away from this talk and then go, it happens that Ed described the exact framework we're going to use, is because there's so many different ones out there. You probably end up very likely to end up with a different one. But what you find is the actual activities are all the same in all of these different frameworks and standards. The activities you need to do, generally speaking, boil down to the same things. Okay, so there are some secure development lifecycle frameworks available to follow as a sort of prescribed, instruction manual. But rather than just describe one of those, as I say, I'm going to sort of try and keep it more engaging by just describing what your team, or you, if you're a developer or project manager, what you would actually be doing in general terms. And as I mentioned just now, if you do that, when you come to try and get certified to a standard, you'll find that that's a lot easier if you know what the practices are and you're following them up front. Because it's almost always the case when you go to get certified, that involves being audited. And what that means in practice is somebody comes along with a questionnaire that's supplied as part of that standard. And then they have to interview different members of the team. And the questionnaire sort of follows the pattern. Have you done this? Do you have a process for that activity? And it's not enough to just fill in the yes, no column with ticks. You have to provide evidence. You've got to include documents and snippets of code, or sort of, yes, we have a work procedure for that and it's here. And if you're following these a sort of a good set of secure development practices, you'll find that when you're doing this audit, all of the questions just make much more sense, and that you already have all of the evidence you need, and all you need to do is just take it out and put it in, put it in a pile for the auditor to see. So I'm going to cover, as I say, at a high level, what activities the development team actually need to do during a project to make sure that the security is kind of baked into the process. So if we look at a standard development life cycle, you've got the standard 5 stages that everyone recognizes there. Now, this could represent a whole project as kind of a waterfall project, or it could be a single sprint in an agile process. So, that might, what you see there on that slide, that might be 2 years of project, just straight linear, one stage then the next, or it might be a 2-week sprint. Okay. Now, regardless of which way you want to do your project, agile or waterfall, that I'm not going to open that can of worms here. A development that follows either methodology, can be expected to follow those stages in that order, either in one shot, or repeatedly, as repeated sprints. So what I've done there is I've added around those stages the practices that you need to follow as part of, as I say, any general secure development lifecycle framework. you know, or what you'll find is that the standards basically ask you, are you doing these things? And the answer needs to be yes to get the standard. So at the top there, you've got activities which are ongoing during a project, but they're not tied to a specific stage in development. So training and risk analysis just happen all the way through the project. They're not, you know, they're not dependent on now we're doing requirements, for example. And then at the bottom, continual process updates should be happening all the time, independently of any particular project that's going on. So I'm going to give an overview of the ongoing activities which are tied to a project, but not at any particular stage of the development. So as you see, I've kept that diagram up on the left there, just to sort of give you a little map to help keep track of where we are in the development cycle, because there's you know, there's a few practices to talk about, so it's quite easy to think, well, where are we in the project again? So you can tell at any given stage where we are in the project, in you know, a hypothetical project. Training, first of all, when it comes to the question of who has the job of making sure the developed product is secure, I'm going to use Phil's answer to this. Everyone is the correct answer. But what you tend to see is there's an instinctive approach of giving one specific person a special role in the project for handling security. And the problem with that is, if that's all you do, if you assign that one person, everyone, and then tell everyone else in the team, you know, your focus, you know, that one person does security, 10 other people, your focus is to, you know, do the development, make sure you meet the deadlines, get the thing working. That's not going to work, because you'll find that security person will be kind of struggling to hold back the momentum of the development team, and they kind of end up sort of tickling around the edges of the security while they're off, you know, churning out lots and lots of code, and you know, one person won't be able to keep up with that. So what you need to do instead is put security in the minds of everyone on the project, all the developers, everyone, any testers on the project. How you do that? Of course, you train them. You know, give them training in secure development, so that you're at the point where everyone is considering security and the practices coming up that I'm about to describe before they consider anything to be done or working on a project. You know, in Agile, you've got a definition of done, and ideally you want that definition to include the activities that I'm about to describe. And of course, the training can happen at any stage. You know, people join and leave anytime, so don't wait for a particular moment. You know, get people trained up as soon as the opportunity arises. And the other activity that's sort of ongoing during a project is risk management. And everyone always talks about risk management when they're talking about developing secure systems or products. So just to give you a very brief overview, when we say risk, really what we're talking about are two things. Primarily the risk of possible vulnerabilities in the final products, which could be exploitable. For example, that would be, you know, in the final design, the final end result, the cryptography keys are too short, and they can be brute forced. You know, this is like a simple example of something wrong in the end result. Secondly, when you talk about risk, We could also be referring to the risk of things happening during development, which increase the chances of the vulnerabilities getting into the end results. For example, we've got a developer who's an expert in this specific area of the system, and they're leaving, so we need to get another developer to work on that bit, and they're not as familiar with it, so they might not recognize mistakes related to security in that area of the code. They won't spot them so easily in code review and so on. So the big aim with risk management is to identify problems in the design or in the implementation as early as possible and resolve those problems earlier in the development cycle. But a second key advantage of assessing risk is to see where the attention and the focus on security should be in later stages. And there's a few risk-specific stage practices in certain stages where I'll elaborate on that slightly. So when it comes to sort of identifying risks, understanding the context is very important. So people who are, you hope will be identifying the risks should be the people who know where to look in the project. For example, what files to look at, what people to talk to, where to look in the design, for example. So if you just identify a risk and say, oh, that looks like it could be a problem later on, and you just note it down somewhere, that's not actually going to help anyone or achieve anything. You need to track the risk and manage it. That's why it's called risk management and not just risk identification. You need to first you do need to identify three things when you picked up on a risk. What are the chances of it happening? What's the impact if it did happen? And how are you going to mitigate that risk? How are you going to fix the problem or avoid the risk in the final end product? And again, this it's important to understand the context in order to be able to do these things. So if you're talking about the impact, it's very useful if you can quantify that impact as perhaps a financial figure. So if you said, oh, if this thing happened, the company would lose X £100,000 or dollars. And that's very useful when you're talking to stakeholders who, are making business decisions based on financial values. Is it worth investing this much to avoid this potential loss, etc. So you need somebody, with an understanding of the business, but also in the kind of likelihood of something happening. You need people who understand the technical goals of the project. Where and how the device or the software is going to be used. So it's very much a team effort to get all of those people together. And the most important thing, once you've identified those three things, is to track the risk to ensure that the mitigation gets implemented at some point during the project. So track the progress of the mitigation. Now, there are stages, which I'll describe shortly, which aim to identify risks specific to a stage. But during the project as a whole, if you were to ask who is responsible for identifying the risks, once again, it's everyone. But usually only one person would be responsible for managing the risks. And that's, the most obvious benefit of that is if you've got people identifying risks, first they know who to tell, and then that person who's responsible for that makes sure that there aren't just lots of duplicate risks getting catalogued and they might catalog those risks in, you know, a big notebook or lots of sticky notes on the wall. That's okay if you want to do it that way. Nowadays, people tend to use software to do this kind of thing. And because the mitigation of a risk more often than not takes the form of basically more work to be done. It's like, well, to avoid this thing happening, we're going to do this in, you know, in the design, in the software, in the code base. And so that ends up being more stories or tasks in a project backlog, for example. So tracking risks which generate more work to be done in the same system that you're already using to track the work in general, that fits neatly together. So therefore, you know, if you're using Jira, which is quite a common solution for tracking your work, a plugin to also track the risk generating more work in Jira, a plugin in Jira to do that makes sense. And also, because you want to track the progress of your risk mitigation, if you're in the same system that you track the progress of all your other work going on in the project, you know, it all just fits together and makes more sense. And of course, not everyone's using Jira, but you know, there are systems, very plugins for similar works. So I'd recommend the first place to look for a risk management framework is as a plugin to the work tracking system that you're using. So let's have a look at practices which are tied to a particular stage in the development cycle. And the first one is during requirement capture. So let's say you're doing a project, you've started the project and you've captured requirements for what the end product needs to do. Okay. Or if you're doing, you know, an agile process, you might be at the point where you've just defined the acceptance criteria in a story that's about to begin at the start of a sprint, or during backlog grooming. Straight away, you can do some security analysis on those requirements. If a device has to operate outdoors in a quiet area, there's a risk of someone stealing the device. Okay, you can identify that risk just from the requirements. And you know, in that example of somebody stealing the device, you know, you could mitigate that by ensuring that, you know, if they stole it and had complete uninterrupted access to it, they couldn't use that time to pull secrets from the hardware or something that they could then use to sort of hack other units that are deployed in the field. So, you know, straight away you can identify some risks just from what does the product need to do. And you put those risks in the risk management framework, you score them, you prioritize them, you plan a mitigation strategy for each one. And the first thing you can then do is mitigate those risks by adding more requirements, okay, security requirements. And doing that at this stage, ideally, when it comes to security problems, avoids anyone having to utter words like, you know, the concept of this product is just fundamentally flawed, or, you know, in order to achieve this concept or this aim in the project, you know, we're going to have to do a major rework of, you know, the whole code base. Yeah, I give a few tangible examples as I go along to sort of try and make this all a bit more sort of relevant in people's minds. You know, a common requirement might be product must only run signed firmware images, and that avoids getting too far into the project without hardware that can provide that in some way, like secure boots. And what you then see, is that the hardware is very carefully selected, and somebody might choose a system on chip with great secure boot functionality. The trouble is then the software kind of ends up, in sort of early prototype stages. It gets designed or it evolves during the implementation in ways that don't actually utilize the secure boot functionality in the chosen hardware. And then you get to a later point in the project where you're like, yeah, in order to actually turn this secure boot peripheral on in our chip, we have to now do a major redesign of, some of our software. But if it's made clear in the requirements early on, it will have to do this. It should sort of be in developers' minds that, you have to avoid precluding the use of this functionality in the chosen hardware. So let's say you've got your requirements figured out and development moves into the design stage. Some design documentation has been created, okay? And just like for requirements, the next practice for security is to analyze the design for security risks. In practice, what that means is, what it could mean is you look at the architecture diagram that somebody's created, or any other design material. Lots of different types of diagrams you can create, and you pick out which parts are at greater risk. And it might just be that you draw red boxes around those and go, those are the risky bits. What do you look for specifically to draw red boxes around? The main thing is input and output of the system. So not just hardware I/O, which is sort of the most obvious one, but anything that interfaces with an entity outside of the system's control. So users is again an obvious one. Other hosts over a network. Typically, a lot of early IoT devices would talk to a firmware server to download a new firmware image, wouldn't authenticate it at all, wouldn't check any signatures, just blindly download the firmware and flash itself with whatever arrives. Also, things like peripherals that you can plug in to your product. Okay, so what should be untrusted peripherals. So if it's got a USB host port, for example, and any USB gadget that gets plugged in there could be hostile. Many microcontrollers out there let you build your own USB gadgets, and you can put whatever crazy packets you want down the bus in that microcontroller, and you can fabricate something and plug it into your product, and you might find all kinds of unexpected things happening at the USB device driver layer. So all of that should be untrusted, as an example. Another example, GSM modems in the past, or baseband modems. If you have an applications processor, you put the modem in your product alongside it. In the past, vulnerabilities have been found in those baseband modems. More often than not, you don't have any control over the firmware that's provided for those. So, your application processor in that instance shouldn't trust messages implicitly that come from the modem, because there's no guarantee of, that modem hasn't been, corrupted in some way. So after identifying risks in the design, as with the requirements, the next thing is to identify risks in the design. Okay. And a common example of a risk you might identify in the design is one layer in a system, assuming no authentication is needed because another layer handles it. Okay. There was an example of a make of car where each vehicle connected over a VPN to like a self-hosted cloud infrastructure that the car manufacturer was using. And a researcher found that if they got access to a shell, command line shell in their car's controller, they were able to issue commands because it had already connected via the VPN, not just for their own car, but for anyone else's car that was also connected to their network. So, based on the risks identified in the design, an initial mitigation may be to modify the design to minimize those risks. Now you might think, well, why don't you just do this all in one go? Because it'd be quicker, right? Than just sort of make a design, then identify risks, then go around again and fix the risks in the design. You know, and you might be able to turn these things around fairly quickly. But if you do it formally and document that you're doing this as a separate stage, again later on, when if you're doing a security audit, you can point to that and say, look at these revisions of our design. You know, we've done these stages that your standard mandates, and it's all much easier to do if you anticipate the need for it up front. Okay, and the last step during the design stage of the development life cycle is defining tests, and specifically defining security tests. And usually in a large project, you'll have testers who are at this point planning out what tests they're going to create and run. And it's simply a case of adding more tests, you know, for security. And if the testers are like, well, what security tests should we do? Well, you can point to the security requirements and say, well, test to these requirements that we added specifically for security. So now that you've figured out, you know, as in any normal project, what the system should do, you've got requirements, how it should do it, you've got a design, it's time to write some code. But before you do that, make sure everyone on the team is using the same tools and setup. And the most common example people point to, because it's the most obvious one for security, are compiler flags. You know, every time the compiler builds a source file, there's various flags you can provide to a compiler now to make it make the output more safe and more secure. The stack protection compiler flag, you know, will prevent crashes being adapted by an attacker into, you know, going from a crash to injecting executable code if there's a buffer overflow. But what you need to ensure is that everyone is using that from the beginning, because you don't want to end up in the situation where you've got a load of code written and it's all been merged into your trunk branch, and then somebody goes, oh, we should turn these flags on, you know, because security, you know, and then you turn the flags on and it breaks the build in about 1,000 places, and then there'll be a big meeting between many of the team where they'll decide, oh, we don't really have time to fix those 1,000 errors right now, so we're just going to leave the flags turned off until such time as we have spare time available to sort that out. And that'll probably happen, you know, a year after the product's been released. So make sure you do that on day one, or as close to day one as you can, and then you know, the errors will fix themselves before they get written by the developers. And so, okay, some code gets written, okay. and there's a code review. Fairly standard practice. Okay. For security, though, it's generally mandated and very much recommended to use a tool, a static analyzer, as part of that review process. The type that seems to suit most organizations, most project teams, is a solution that can run on a CI server, self-hosted or as a cloud service, but basically so they can run in a CI pipeline, run on the code whenever the code's pushed on the topic branch, or whenever you create a PR to merge that code into a trunk branch. It depends how you want to run the project, but basically something where before a developer can get their code approved and merged, it has to have gone through this tool. That's the ideal setup. Now, some tools, I've listed a few on the slide. Some of them will just look at styling of code, kind of layout, code conventions, etc. Now, other tools are much more advanced, and they'll use something called a meta compiler to kind of build a model of the code that can track variables in memory and so on. And that a tool of that class can inspect and follow variables and the data that the variable sits in as it goes through different source files, in and out of structures, through pointer accesses, and so on. And by doing that, they can effectively spot like a buffer overflow issue, which typically the setup of a buffer overflow happens. It doesn't happen in a canned example. It's like, here's the problem. It's in many files where, it's read over there. The length is figured out over here. It doesn't depend, it doesn't depend on the right value that, is being used by some user input. So it's, yeah, it can sort of try and tie all of that across different source files and highlight a problem very effectively. However, a tool is not a replacement for a human inspection. Even the best tools can only really recognize patterns in the code. Patterns, it's like a buffer overflow, as I've just described. But in order to recognize an architectural flaw, for example, this code is written as if we trust this data that's coming in from over here, but we shouldn't. We should run more checks on it. We should force an authorization at this point before we do this operation. A sort of pattern matching tool won't recognize that, because that takes a human, somebody who understands what that data coming in represents, what the source of that data represents in kind of the wider context of what's going on in the code, in the device as a whole. Now, the problem with human code review when it comes to security is that in a complicated code base, you can spend a long time scrutinizing it for security, and you never really know if you found all the issues. It's like searching a haystack for needles, but you don't know if there's any needles in there. So, when do you stop looking? So what you need to do really to sort of rein in that effort is to sort of rely on the risk analysis done at the design stage to indicate, which areas of the code base are the risky ones, and sort of concentrate the efforts onto those. So into the testing phase, and I should note that in many projects, testing can be an activity which kind of goes on pretty much all the time. If you have a test team, they're not going to just start and stop because somebody's got to the testing stage in their feature and whatnot. However, once I've sort of put this practice in the testing phase. That's generally about the time when you want to do this. Once the feature is sort of nearing completion, you've got enough code in that's been approved and merged that you can sort of understand the implementation that's been created. That's a good time to check whether the results, when you compare it against what was intended in the design, whether they match up. Because there's nearly always some variation from design as soon as the coding begins. Now, ideally, any problems in the implementation will it be caught during the code review, or when checking on the progress of mitigations of risks, you might fix up problems. So just a full evaluation of, okay, we wanted this feature, let's see what's been done, let's compare it against the risk analysis in the design. It's just like an extra step, an extra check to make sure that nothing slips through. Now, if the name reevaluate implementation against security design analysis it's not very catchy, that's more my descriptive name of what you do. If you look in like the Microsoft Secure Development Lifecycle framework, they call it attack surface review. So, but if you read their description of what an attack surface review is, it's basically it translates to my longer description there. Now, once you've got enough of your products implemented that it kind of does something recognizable, it's generally very popular to go and get it penetration tested. Now, this is an extra assurance. You shouldn't just rely on this as a sort of as the security measure in your development. It's very much a reactive measure. The other things I've just described are proactive practices to prevent problems starting in the first place, whereas this is like, have any problems made it through into the final implementation? Now's the time to get somebody to find out. So a fresh pair of eyes on the situation. You might think, why don't we just do it ourselves? It's quite rare to find software developers who are kind of really well practiced at breaking into systems. It's a similar interest area, and there's a lot of overlapping concepts. Good hackers know how to code, but it's really a case of what activity is a person focusing on day to day and kind of honing their craft at. And because of that, pen testing is generally outsourced to people who focus on hacking as their everyday activity, their professional vocation. Now, when you engage a firm to do your pen testing, you'll need to tell them which parts are in scope and what's off limits. You might say, just ignore that JTAG port that's just hanging out the bottom of the case, okay? And what you need to do, what they'll ask for is some documentation. So if you're saying, I want a black box appraisal, so as if you're just somebody buying the product, and they'll say, okay, just give us the sort of standard user instructions, the user guide, and we'll go from there. Or if you're not really done yet, you might say, can you just look at this particular piece within the system? In which case they'll probably ask for source code, more technical development documentation, and so on, so that they can just start at the boundary of that subsystem. Okay, so the time, let's say in the project's life cycle, the time has come to make a release to the public. If it's the first time you're making a public release, you need a plan for what you're going to do if there's an incident. An incident is basically if a vulnerability is found and disclosed to you by somebody outside of the company. So what you need is a contact address that's clear and visible to the public. You know, this is who you contact, an email alias, if you find a vulnerability. And then from there, you'll want to plan in advance of who's you know, approved to make a public announcement. What are they allowed to say? What should they definitely not say? That sort of thing. Now, doing that and having a good proactive response planned out is not only good for users of the products, because you know, when somebody makes a disclosure, if you're proactive, they're much more likely to be willing to give you some time to patch it up and make an update before they go public with their disclosure. So it's not only better for the users if that happens, but it's also good for the reputation of your company, because you know, the security research company that found the vulnerability, or just some hacker, they'll go, you know, they were really responsive and they've got a really good policy for this, so that's a good company with respect to security. So it's a really good reputation boost if you deal with an incident in a timely and planned out manner. Now, if you plan to support a product for a long time in the future, what that basically means in practice is providing security updates. You know, new features have long since stopped years back, but we're still providing updates if there's any security issues that get found. And it might be obvious, but it's worth reinforcing the point that you need to ensure all the tools and knowledge to debug existing versions that have been released of the software, build any new versions with patches that you need to make. You know, all the tools and knowledge to do that are kept safe and archived. And that, you know, when a project enters that period, it kind of seems obvious. But the thing about long-term support is that there probably won't be a regular release cycle. You know, so somebody isn't redoing this every couple of months to keep things fresh. You might, you know, if there's a vulnerability is found, it might be the case that the last release was 5 years ago. And since then, nobody's touched it at all. Nobody needed to touch it. You know, it's just been, you know, the devices that are out there and the firmware on them have just been doing their job. Okay, but now a problem's been found, and the last time anybody did anything with it, all of those people have left the company, or we've forgotten who they were. So it needs to be a really clear archive in place, and you know, an explanation of how to, you know, dig it all back out and make a fix. So finally, let's look at some practices that need to happen independently of a specific project. And it's quite common that companies doing this kind of thing already. It's often referred to as continuous improvement, or a similar name, or it might be, you know, talked about in terms of Kanban. So when something goes wrong, typically, you know, people talk about it as when a defect gets into the final release. You do a root cause analysis. So the point of this is, you know, you don't just fix the mistake, you fix the process that allowed that mistake to happen. From the perspective of security, obviously the mistake is if a vulnerability makes it out into the final release. And as well as that, though, don't just wait for mistakes to happen to improve things. Okay. Best practices in industry change all the time. So a sort of often a mandate of, well, a good thing to be doing, not so much mandated by standards, is to just be always looking and researching in industry. You know, are we keeping up with the best way of doing things? Are there new tools coming out that will allow us to accomplish things better? And basically, you know, keep updating your process and making sure you're doing the best job possible, basically, rather than just waiting for something to go wrong and then going, okay, how could we have prevented that? So to conclude, I'm just going to run through a few common concerns that people hear or say when you talk about this kind of stuff. People tend to say, oh, that all sounds great, but shouldn't we just be doing this anyway? You know, isn't this just common sense? Or, you know, they might say, you know, might look at a particular activity and go, well, that's just obvious. And yes, quite often is quite common to find that some of these practices are already being done by any given project team in a company. But for security and for achieving standards, formalizing it all in kind of, you know, making it, doing these practices in a documented and clear manner, it makes the practices consistent across a team. Okay, and that's important because everyone needs to be working for the same to the same sort of rigorous standard in order to maintain, you know, this approach of ensuring that the security is baked into the process. And as I just said, it provides documentation for the security audits. Now, a common concern is doing all of these extra practices during the development is going to take loads of extra time and, you know, therefore cost loads of money for the company. Now, if you talk about defects, you know, just not just security, but just mistakes entering into the implementation of a product, it's been pretty well established for many decades that if you fix a defect in an earlier development stage during the development life cycle, it greatly reduces the effort required. So you can see that graph there, which shows the general trend where, you know, the cost is exponentially lower to resolve a problem in an earlier stage of development. And security issues are no different. Okay, if there comes a time in a project's life where security suddenly becomes more important and it hasn't been before, you'll probably find, if that point is later in a project's development, fixing all of the security issues at that point will be much more expensive than just getting it right the first time around by using these practices. Okay, so it can be hard to quantify the cost, but if you do it from the beginning, it will be lower than realizing you've got problems and trying to fix them later. Now, people might say, well, we've picked a security standard that we're going to work to. Why doesn't that just tell us, you know, what we need to do? And it will, but it's in a kind of obfuscated form, I would say. Having had some first-hand experience of getting audited and then doing audits to security standards, kind of self-auditing, my advice would be not to let the certification drive your sort of secure by design approach. Okay, so although kind of following a secure development practice in itself doesn't imply a particular certification or standard, you know, many of the ones with framework in the name do try and force it. However, when you go and download the PDF for one of those standards, the explanation in there of what you need to do is not very clear. And what happens then is you'll be sat in an audit and somebody's reading a question and you're wondering what it means. And then you go and check the guidance document that comes with the questionnaire and it's got an abrupt paragraph that still leaves everyone kind of puzzled. And the most problematic outcome of that is you go, well, you know, what's the minimum we need to do to get past this question in this audit? And it sort of devolves into a bit of a box ticking exercise where you're effectively just trying to work around these demands for certain processes or certain documentation. That's the worst case. The sort of slightly less bad, but still very problematic problem is lack of evidence. So you get to an audit, you don't have the evidence there to get through the audit, and suddenly you've just got a massive effort hurdle to get over, where somebody turns around and goes, right, we want this standard, you all need to go away and get evidence now, and everyone has to sort of down tools and go away and construct evidence that they've got a secure development here. And what happens then is you just get a team of developers who are very resentful of the fact that they have to stop writing code, stop doing their interesting job, and go away and make evidence to get a security standard. And that just builds resentment. Whereas if you start from the beginning with the training, you know, everyone knows why it's important. They know what they need to do. As the development goes on, they've done that. And when you get to the audit, it's all already there for you. So I can't really emphasize this enough, that if you take a proactive approach, which is driven by sort of training and education, people understand the benefit of doing this, and the audit is really just a check of that you have done it, rather than forcing you to go away and do stuff. So that sort of wraps it up. Thank you for your attention. Let's go and see. I've heard a few noises in the background, so I don't know if there's any questions.
Thanks, Ed. Yeah, we had a question from Rune. I think Nick's had a look at it in the chat, but we'll ask it here as well. Is it possible to train everybody to be a security expert in the team?
Well, the answer is you don't need everyone to be a security expert in all of security. You only need them to have security awareness in the role that they're playing in the project. So if they're a developer and they're designing, or if they're an architect, they're already more of an expert in the team. So they have to be more of a security expert, I'm afraid. That's just part of the job. Okay, if you want to hold yourself up as a, I'm capable of architecting the system that we're going to make. Okay, you need to take on the burden of being okay, and I'm going to do that securely. So that's more security expertise than a junior developer who arrives and goes, I'm going to take a story off of this backlog pile or this sprint, and I'm going to go and implement it. And it says in there what I need to do. You only need to train that person up to the point where they can write code securely, okay, which is less less in scope than being, someone who can architect securely, okay. And the training for, a project manager would be different again. We're not just talking about the project team. You do also really need to train your stakeholders, so that they understand why you need to spend extra time and money doing it right. Okay, so it's sort of different slices of security training for the different roles in a team and in an organization.
Absolutely. I think that's a really important point there as well. We're not just talking about project managers and developers and architects here. It's all stakeholders in the project, from the decision makers, people with the budget responsibilities, the purse strings, the customer that we're working for here.
Good point by Rune.
Real quick one, Ed, before we dive into James's talk. Do you think there's sort of this might not be easy to answer. How much overhead do you think sort of adding in a secure development lifecycle is likely to add to a project?
I'm not just going to put out a figure or a percentage, which I think some people want is like, oh, it's going to add 20% to every, to figure out what 100% of the cost is and then add another 20%. Maybe that's the right answer, but I think it really depends on how well your development team do the job. Okay, because if somebody says quantify the cost of just doing the project before you think about security, for one team that's a much lower cost because they work together like a machine and they just get the job done right. Whereas another team, for whatever reason, they'll struggle with the same project and run on years late. Okay, so if you've got a really finely honed team and then say, oh, can you just do these other things as well? If they execute those extra tasks really well, it's probably not that much more work because, I mean, for a start, they're probably doing a lot of those things anyway. I think by now everyone's already doing code review out in the world, right? Okay. And continuous improvement and a lot of these things, but you just say, and also think about security as you do those things. So I would say the short answer is, if your team is already doing a really good job, probably not much extra overhead, I would say. That's an optimistic answer.
I think I'd extend that as well with a different way of thinking on it, maybe on the, I'm not sure I would consider it as an overhead. If you have a genuine need for a secure product, and a secure development lifecycle is a proven way of achieving that, I'm not sure I would consider it or communicate to stakeholders and others around it as an overhead, because it can be seen as something you can eliminate and get rid of. Overheads are often seen as things you can optimize away. And if it's truly necessary, which it is in a lot of the scenarios we're talking about, I think considering it as an overhead can make it more challenging to get the stakeholder buy-in that's necessary to make that a success. Right, we are. Oh, Nick.
I was just going to say, depending on the the required assurance level has like a big impact on this as well, and that may be in terms of third parties performing some of that work, like pen testing and the likes, but those are still going to be performed at various iterations during your product development. So that's going to have an impact that needs to be factored in.
Good point.
Yeah, I should also say just quickly that various of those practices you only need to do one time. I should have maybe clarified that as I went through. This is a one-shot thing you do at the beginning, whereas this is, something you do every sprint. So, getting everyone set up with their tools correctly, ideally you only need to do that, one time. And then anyone who joins later, you just say, follow the instructions in this documentation to set your tools up exactly as they should be. That's basically a no overhead task. Set up your CI/CD to run your static analyzer. That's something you do one time, and then it's just there and it's running. So those kinds of things, minimal overhead. Whereas sort of, let's check the implementation against the design and make sure that they don't diverge. That's something that you will have to do repeatedly every time new features get implemented.
Good point. Thanks, Ed. So we're on to our third and final presentation for today. James is going to take us through securing IoT systems end to end. Over to you, James.
Thank you. Okay, hello. I'm going to talk to you about end-to-end security for the Internet of Things. We're going to look at the roles of the main components of an IoT system and how achieving end-to-end security is dependent on the relationship between them. In that context, we'll explore ways to determine what the threats are and how to define and evaluate those risks in detail, and also how penetration testing can provide assurance that our system is secure. Most of these subjects are expert fields worthy of in-depth discussion in their own right, but I will try and give an idea of how they fit together in the time I have. So the Internet of Things has brought us a wave of connectivity. These graphs are just to illustrate that although there isn't really a consensus of how big it is, that it is clearly big and getting bigger. Instead of the internet being essentially comprised of computers serving humans directly, there's now a growing range of connected devices, all semi-autonomously producing and consuming data and doing things in the real world. So while traditional cybersecurity has been a hot topic, IoT security has often been a bit of an afterthought. Vendors have had to balance developing secure systems against shipping product, and system builders may be tempted to integrate third-party hardware that doesn't necessarily follow best practice. And although there are emergent standards, as Nick's gone through, there isn't really consistent security implementation across this pick and mix field. And in this fragmented ecosystem, there's a potential threat surface from every hardware or software component, every channel of communication, and the users, of course. So there's been a 100% year-on-year increase in IoT infections over the last 3 years, and IoT botnet activity has been one of the major security trends of 2021, along with supply chain attacks. And while user management and cloud services are relatively mature, the devices and gateways are innovative technology at the physical frontier as well as the edge of progress. And although connected devices can be independent of any cloud service, presenting their own authentication and services to a connection, I'm going to characterize an IoT system by simplification to 3 principal actors: the user, the cloud service, and the devices. There are other potential configurations. There isn't really a one-size-fits-all IoT, but the principles of sound security apply throughout. These actors are supported by the service platform provider and the connectivity service provider, although the main trust relationships exist between those principles and can be entirely independent of those supporting casts. So the users and facilitating applications are likely to belong to a complex multi-tenant role-based architecture, including potentially resellers and their customers broken down into tiers of individual users, and the applications used as part of that system by them. Cloud services maintain and model users and devices, their relationships, and they moderate communication between them, managing access to control and data features, commissioning and provisioning devices, and mediating access. They can also implement business logic, data processing, storage control, storage services, control and monitoring of the devices and the users. The devices can be discrete and self-contained or form part of a complex local network connecting to the cloud through an edge gateway. An edge gateway may perform some logging, processing, and monitoring itself to lighten the load on the network and cloud service. So communicating across the borders between these 3 actors requires trust to be established in their relationships. The communications depend on the platform and connectivity providers, but confidentiality and integrity of the trust relationships between those main players depend on giving them the means to ensure integral security within the system. There is another actor that needs consideration: the bad actor or threat actor. From simple user error to advanced persistent threats, the bad actor is any agency that threatens the integrity of the system. To better understand that situation, it helps to have intelligence. Threat intelligence. Now, this is a term for an important tool for building and maintaining a secure system. Threat intelligence is a wide field within itself, tailoring a solution to your own domain by aggregation of appropriate sources is key. There's a community, or communities in fact, devoted to sharing knowledge of domain-specific threats to hardware, software, and network security. Increasingly, machine learning and artificial intelligence is being used to process logs of system events and highlight discrepancies and pattern match against known attack profiles. It can pull up any sort of anomaly. So This definition of threat intelligence comes from Gartner, but essentially we're talking about up-to-date information used to understand potential threats to organizational assets. This information can be used to inform the response to those threats. Good threat intelligence prioritizes current investigations, but it can provide analysis of past incidents, and it enables the monitoring of infrastructure for repeat attacks. It allows a proactive approach to risk rather than a reactive one. Knowledge sharing within the security community is a valuable source of it. This is a really good starting point, the Open Web Application Security Project Top 10 Vulnerabilities. And if the least you do with your product is to go down this list and mitigate any weaknesses, you'll less likely be presenting low-hanging fruit for an attacker. And most of these vulnerabilities can be secured using tried and tested principles of security. I'm not going to go through them individually because time's a constraint, but if you've got any specific questions about them, we put them in the comments and we'll address them later. So building and testing for security. Using public key infrastructure, PKI, enables confidentiality, integrity, and authenticity. This means that in a communication between A and B across a network of unknown security, that the sender can be confident in the identity of the recipient, that the information between them is not available to other parties, the recipient can be certain that the communication comes from the sender, and also that the contents of the message has not been altered. Zero trust. Zero trust architecture is an approach where the assumption is made that the network is hostile and that there is no inherent trust. This fits very well in the IoT space, as the commodified components are likely to be installed in environments with completely unquantifiable security. By using the principles of zero trust architecture and designing a system, we can have confidence in the CIA, as I think Ed mentioned, because every transactional request is verified based on an access policy. Supply chain attacks are another current trend. A supply chain attack can be anything from breaking into a factory to hacking malware into a build system, which is thereby distributed to customers. And in providing the broader industry with apps, devices, and systems, the IoT industry has its own supply chain. So if an attacker can gain access to any part of the build, malware can be distributed within the system itself. And Ed's talked about how important it is that security analysis is incorporated into build pipelines, which will prevent known vulnerabilities from integrated in a continuous integration cycle. So individually, users. User presents the most obvious attack vector, but we can embed unique identities into devices and cloud services, but the user is often a generic client accessing the system via an API from a completely anonymous location. So it's important that the user and the core system can identify each other with confidence and communicate securely. We can enhance security by constraining passwords. We can use multi-factor authentication. We can offload some of the weight of developing that through using federated identity services. But the security of user applications is ultimately dependent on the authentication and access granted by the cloud services. We shouldn't store data outside the core system unless it's absolutely necessary, because not only does it get obsolete very quickly, but it's at risk. So really, where we can, we rely on the system to provide live data. The cloud service needs to effectively implement and mirror edge device security. The system must enable inventory and containment of all the agents within it. This means it needs to discover, monitor, manage, and update devices from initial provisioning throughout their life cycle, and that can be years, so it needs to be considered. It'll need to provide updates to software and credentials, as well as to facilitate functional control and measurement features of these endpoint devices. The cloud service is really the core of system security. Role-based access control for users helps to minimize risks from human error or intentional breaches by assigning and managing appropriate levels of access. So if a mobile app client is compromised, or indeed a user is compromised, the attacker won't be able to elevate their status within the system and access things they shouldn't through that API. As a matter of course, a secure transport protocol such as HTTPS should be used, but PKI can enable security for software updates. So even if an attacker has gained physical access, to the board of the device and dump the firmware, they won't be able to access the they won't be able to replace it with modified firmware. So we need ongoing threat intelligence. Security is dependent on continuous risk management, balancing criticality, cost, usability, and effectiveness. We need to monitor and analyze internal logs. This is where machine learning and artificial intelligence can be applied to pick up anomalies that may add to our security picture. But we also need to leverage the community to have an awareness of new external threats, emergent published vulnerability. So we come to devices. When a device is manufactured, it can be assigned a securely built-in identity. Secure cryptographic credentials burned in at manufacturer authenticate the device to the server, and importantly, vice versa. So confidence in the identity at both ends allows zero-touch onboarding, secure provisioning, and remote management. On first boot, the device can authenticate against its trusted platform. When the connection is made, the device can be further configured and complete the onboarding process. A secure means of update management is important. We need secure access, and as has been mentioned, we need to digitally sign updates and check that signature at the point of updates. Preventing rollback is really important. If a device is running version 5, which has been updated because of some vulnerability in version 4, if a hacker was to obtain a secure signed binary of version 4 and then push that to the device should say, no, that's version 4, because otherwise the hacker will be able to upload a vulnerable build and potentially exploit not just that device, but the whole system. An edge gateway is a device that controls the flow of data between two networks, for instance, your local area network and the cloud service. It can be data from its own interfaces or from a dependent network of things. In the later case, there'll be a wired or wireless network that needs to maintain an acceptable level of security in that operational context. Increasingly, devices form part of a local wired or wireless network with their connectivity moderated by an edge gateway. But whatever the system topology, the vulnerability assessment, which I'm going to talk about in a minute, needs to consider the threats and risk across that whole attack surface. Sensitive functions on the device can be run in a trusted execution environment. As well as an irrepudiable identity, devices require built-in hardware and software security features to manage data securely and prevent root access. So a strong root of trust is essential. The root of trust is a set of functions that the rest of the system can use to ensure security. Often implemented in hardware, the root of trust forms the foundation of on-device security. It gives the device autonomy to safely, hang on, sorry. Good, sorry, back again. It gives the on-device security. So the device has autonomy to safely use public key infrastructure to authenticate and perform encryption on the data that it consumes and uses. We can achieve secure provisioning and reprovisioning, both of software and security credentials. It's sometimes important to prevent or at least monitor tamper detection. There are some hardware root of trust, provide special switches for this. If a device is to have a cellular connection, either as principal connectivity or as emergency fallback, an integrated SIM is a security enhancement, although it does potentially affect versatility. We also need to look at the security of any short-range RF communications, such as Bluetooth, Zigbee, Sigfox, LoRa. The security of those protocols need to be considered in the use context. What can a hacker sniff? Is that protocol actually secure enough for what we want to do? So this brings us to the evaluation of threat and risk. First, it may seem that the possibilities for attacks on a system are unquantifiable, but a bit of effort spent at the early stages can break this down and provide useful knowledge and reveal potentially structural issues within that system. So to give an overview of how these threats can be enumerated and valued, I'm going to give a brief breakdown of attack tree methodology, as it's relatively simple and flexible. To do this process in depth will take much more time than I have, and there are many more approaches to threat modeling. But hopefully I can show how value mapping threats helps to direct development efficiently. Now, on your screen now is the classic example of an attack tree for obtaining the contents of a safe from Bruce Schneier. Not actually Bruce Schneier's safe, he did the diagram. As you can see, the various potential paths to opening that safe are ruled out, considered impossible or too costly, leaving two options really of bribery or safe cracking. So we could expand the required processes required to gain access to the safe and cut into it and cost each node in that branch. I'm not going to do that, but it should give you an overview. To start with, we basically consider the target system as a whole, so we're not going to look at a safe. We identify the possible attack goals, listing potential threats at a high level and assigning an impact to each root threat. So examples could be obtain the contents of the safe, view the camera feed, control the lights, open the lock, read the sensor data, corrupt the sensor data, or simply destroy a device at the end of it. Each threat on that list is then rehearsed, determining each necessary action or potentially multiple pathways to its success, generating an attack tree, which is a conceptual map of potential paths to attacks on our asset. This is done in the context of the environment, organizational security policies, and assumptions about the physical environment and the physical security of components within that system. By each potentially successful branch of the tree is then evaluated node by node and costed to work out the minimal cost for that attack to the perpetrator. By analysing the requirements of an attacker's path to success for each root threat, we can evaluate the impact to the enterprise over the cost to the attacker for each identified threat. So this can be considered against the resources necessary for mitigation. Mitigations discovered or derived by this analysis to prevent an attack path entirely or make it untenably expensive to the attacker become security objectives. These mitigations are security objectives to the product and or the environment. So this process will help to develop direct development to create the most secure system possible with the available resources and hopefully give an understanding of any remaining vulnerabilities. Now this vulnerability assessment is an important document if the product, well, it's an important document regardless, but especially if the product is going to be submitted to penetration testing, which we're going to look at next. Penetration testing is a method for gaining assurance in the security of an IT system by attempting to breach some or all of that system's security using the same tools and techniques as an adversary might. That's the definition from the National Cybersecurity Center. So it can be a valuable addition to threat intelligence, but it isn't the most effective way to discover vulnerabilities. If you submit a product for pen testing, you should really expect that the results from the testers will actually conform to and confirm your own vulnerability assessment. Your own internal documentation of threat and risk, as discussed, should be shared with the testers while defining the scope for testing. It's really not appropriate to view pen testing as a primary method for achieving security. That should be a consideration throughout the planning and development of any device, service, or system. So, testing will look at a range of potential paths to access, from board tampering to compromising the communications with an edge gateway or a cloud service. There's a wide range of software and hardware tools available, and they're available, of course, to hackers as well as penetration testers. There are different approaches: white box, black box. There are 50 shades of grey box in between, and the nature of testing should be determined to be the most appropriate for the intended scope. So a typical methodology for pen testing is to determine the scope, to map the attack surfaces, then to actually perform the attacks, the vulnerability assessment and exploitation, and then documentation and reporting is what really provides value to the customer of the pen tester. So determining the scope is negotiation. It's dependent on the nature of the product and the result of a discussion between the maker and the tester to provide value from the process. With the complex stack of an IoT system, it's likely that different approaches will be used for different elements of the system, but it's important to coordinate that approach so that vulnerabilities that may exist in the relationship between different parts of the system are analyzed. As well as software, hardware, and network vulnerabilities, processes and end-user behavior can be seen as in scope. Testing one element of the system in complete isolation may be valuable when you're introducing a component to an existing system, and determining the scope for that should take account of any vulnerability assessments for that wider system. Scoping of the test will establish the methodology to be used. White, grey, or black box refers to really the amount of information the tester is supplied with about the function of the subject. As Ed's talked about, the tester may be asked to investigate specific attacks from that vulnerability assessment. To give realism and perspective, as well as looking at the device in physical isolation, setting the scope for testing may involve negotiating access in an operational scenario, potentially involving a reboot or a firmware upgrade when a device could be most vulnerable. So the scope of the test is the result of a negotiation between the tester and the maker to deliver value from the testing process. The next step, attack surface mapping, involves the reconnaissance and discovery of potential entry points that could be exploited, and that work is dependent on the scoping and the methodology used. The more information that testers given at that stage reduces the work they'll have to do in discovery. So remember, they're on your side. A viable attack may use multiple surfaces and be iterative. For instance, in a supply chain attack, you can't get to the firmware without physical or network access. But there are three main areas where attacks may be considered. I'm going to list a few examples for hardware, firmware, and network attack surfaces, but the specifics will be very much dependent on the test subject itself. So in hardware, the tester is going to look for potential vulnerabilities and routes to access. They'll attempt to identify the hardware component, research them, and find if there are any known vulnerabilities. Looking for JTAG headers and UART interfaces is an obvious choice. And developing a consumer-safe, secure production board is costly and time-consuming and, frankly, very unusual. And it's probably not wise to assume that simply leaving JTAG headers unsoldered on the board is actually going to deter a determined hacker. They'll also look at peripherals, USB devices, any opportunities to sniff the communication buses. Exposed ports can potentially allow an intruder to gain access and elevate privileges, read and write data, and will physical tampering, enable access to sniff or modify components. In the firmware, they can look for means to dump that firmware or pull sensitive data between internal components. What do they know, or what can they discover about the reboot and firmware processes? Booting up and the firmware upgrade process is often a potential weak point for firmware modification insertion. The network testing is very specialized and dependent on hardware and protocols used, and all that will be determined in the scope. There are innumerable tools available to analyze and crack network traffic, but the hackers will or pen testers will try exploiting those communication protocols that they can find, sniffing radio packets or network traffic, and modifying them, replaying them, fuzzing the recipient, and it's a specialized area. I haven't got a week to go into any significant depth, but the next step is the vulnerability assessment and exploitation, and this is where the tester will actually try to defeat the security of the target using the potential entry points found in the discovery stage. And as before, to some extent, this can be iterative with the attack surface mapping stage. They'll look for sniffing clear text data between components, listening to internal traffic, identifying protocols like UART, I2C, SPI interfaces, and so on, to try and get access to sensitive information like keys, hashes, and passwords. By isolating traffic that's unnecessary for system function, debug calls and so on, open interfaces for configuration or debug can be discovered. They'll look at whether the device is becoming vulnerable during a firmware upgrade. Can that process be hijacked? Are there vulnerabilities in the radio and network traffic? Are there ways to exploit identified communication protocols by jamming or replay attacks? And is it possible to force the device functionality to break or alter? This is all really dependent on the scoping and the attack surface mapping and the device itself. But as a broad overview, this brings us to documentation reporting. The test team should produce a report that will include any security issues uncovered and an assessment of the level of risk that each vulnerability exposes that system to, or that part of the system to. Hopefully, they will include proof of concept, methods, code examples used to create each attack, and a discussion of resolving each issue or preventing it. Also valuable is any advice on the accuracy of the vulnerability assessment you provided, and advising how to improve that process. So pen testing is sometimes seen as a panacea, as a cure-all, but really it's no substitute for a development process that considers security at every stage, but it can be an effective means of assuring the security of a system, but only assuring them. So I'll deal with a couple of things here which come back. Nothing is more permanent than a temporary solution. It's very easy to let vulnerabilities, especially in IoT systems, stem from the development process itself. Debug ports are left open, using shoddy default security, failure to implement secure communications at both ends of a channel, or leaving information that can be harmless in the development lab available to the most casual sniff. And as Ed pointed out, it is much more expensive to fix things when you find yourself dealing with 10,000 products as a worldwide catastrophe than actually on the design table at the beginning. A second pair of eyes can help weed out this sort of problem. Peer reviews of design and code, pair programming, and so on, and of course static analysis, as Ed pointed out, in the CI/CD pipeline. But we need to establish solid trust between all the nodes, encrypt all the communications to protect data, and implement controls for automatic revocation of certificates and security credentials. All communications really should be digitally signed and ideally sent over an encrypted channel. Software and configuration should be at least signed digitally, and that will ensure integrity and authenticity of the systems we're using. And my final point, really, which covers a lot of the issues we've dealt with, is don't try and roll your own. Hopefully, we're not going to try and attempt to create our own cryptographic algorithms, but the point is that there are tried and tested methodologies for authenticating, securing our communications, from root of trust hardware that's capable of generating cryptographically secure random numbers to facilitating key exchange with certification authorities and processes to ensure the security of our networks. If we don't monitor and resolve what first seems like an expedient shortcut, or just gets forgotten in terms of development, if we haven't instigated a secure process from the beginning, this may become baked into the core of a business critical system and later present a threat surface that jeopardizes the enterprise. Fixing retrospectively after failure costs many times more than sorting it properly in the first place. So secure identification, encrypted communications are important for everything, and those security mechanisms must extend as far as possible, as far as useful, as far as necessary. IoT security is pressured due to the rapid pace of development and pressure to get connected devices to the market. But an IoT system will need to support assets in the field for a potentially long time in a changing landscape of user requirements and evolving threats. The borders are expanding. There isn't yet a turnkey ecosystem platform for IoT. It's a wild west. Methodologies to develop secure systems and safely manage device lifecycles do exist, and engineering in principles of solid security will allow a system to evolve to cope with new components, new threats, and meet new standards and protocols. Thank you very much for your attention. So I'll if there are any questions, I can't see these questions. No.
Thank you, James. Excellent. So I can see Joaquin's typing in the chat. We've got a few people typing. So while I'm hoping there's some questions, we did a few people did send in some questions ahead of the workshop. So I'd like to take a minute just to run through a couple of those. So Roman Ruff asked, which tools could be used to simulate an attack on a wearable device to check how secure it is? And I guess we could expand that beyond wearables as well.
Well, we could. I mean, very often wearable devices are going to use BLE, but there are other protocols. There's Ant and Ant Plus, and LoRaWAN is growing in specialized circumstances for wearables, like mines and whatnot. I couldn't find any ready-to-go hacking tools for those two, but there may be some. But a skilled tester may be able to perform security analysis with Wireshark, which is a classic. For Bluetooth, there are many tools available, and some of them come installed with Kali Linux, which is a hacker or pen tester's kind of favorite build. Wireshark, as I say, is important. The hardware tools, they can use a generic dongle or specialized packages, but there are loads of software tools that provide information on a target, from Android apps to command line interfaces. There's BTLE Jam that sniffs, jams, and hijacks BLE devices. BTLE Sniffer is good for hardware fingerprinting. Pen IoT is good for DOS, fuzzing, sniffing, and replay. There's the Bluetooth Stack Smasher, which is a fuzzer. Blue Snarfer, which does what it says on tin, and Blue Sniff, and probably hundreds of others too.
Fantastic. Thanks, James. We've got some great questions coming through. I see one from Bernard. What's our experience with customers? Do we see a clear trend for more demand? Absolutely, yes. Real emerging trend. 5 years ago, security was often an afterthought, not common to all projects. That's definitely flipped now. It's something that we consider is baked into our process for every project. That's something we perform at the start of any project, regardless of scope, is a security analysis, determine what security workflows and requirements are relevant for that project. And that isn't just because we wanted to do that, that's in response to market interest. So yes, it's very much a growing area for us. Question from Joachim Kastner. This is one that you can help answer, Nick. Joachim's saying that in our industrial business, we follow IEC 62443. How does that relate to the standards that you mentioned? Oh, I think Nick might be having some video trouble at the moment. I see he's not with us right now. I'll jump back to that in a moment. There was an additional question from Roman Ruff that I think is worth just talking through quickly. What are the methods to protect over-the-air firmware update process? So I think there's a few parts to this. There's sort of the device side, and there's sort of server infrastructure considerations as well. James, Ed, any thoughts on that?
Well, yeah, I mean, Ed can probably talk more in depth about the chipsets available, but I know that there are chipsets available that implement secure bootloaders and crypto modules. So choosing capable hardware is important for starters. But really, for between an over-the-air update over, for instance, a Bluetooth or Zigbee network, we need to consider digitally signing the update binaries, potentially encrypt them, although that may be redundant if we've implemented useful signing. Using BLE Secure, for instance, to secure that communication. We talked about rollback protection before, and recoverability, so the device will fall back to a working build rather than just, if it doesn't boot 3 times, it's not going to, basically.
Yeah.
So we've got an interesting question from Andreas Geisreiter. Apologies for the pronunciation there, Andreas. This was a question we received in advance. Quite an in-depth one, so I'll try and summarize it quickly. So an STM32 MP1 project, boot chain, sort of boot ROM start, loads of signed first stage bootloader to SRAM, authenticates that based on a fused key in the OTP block. There's next stage, which is assigned fit image into U-boot, and so on, and ultimately ending up with Linux that applies DM Verity to authenticate file system blocks. And the question there is there any advantage or benefit to using a TPM in that case? So I think rather than necessarily answering that specific question, I think this is quite a nice opportunity to talk about not only sort of secure boot, but how things like TPMs and secure elements can be used in a wider context than just boot security. Ed, is that something that you could?
Yeah, I mean, if you proceed on the assumption that your system on chip is going to do your boot security for you, and using the process as just described in the question, where a secure element tends to come into play is if you have internet connected devices, and you want to ensure that you're only selling your official product and not clones. You certainly don't want clones joining your cloud infrastructure. A secure element is very useful for that use case, where you buy batches of the secure elements with the secret keys or the private keys already sort of programmed into them, or generally they program their own private key internally and then just spit out the public key, and you put all the public keys for all of your fleet of devices you enroll them in your cloud infrastructure. So it's a very useful way of making sure that you don't have clones of your product entering the market that can connect to your cloud services. That's generally where system on chips, they do have eFuses, so you can program kind of data onto them. It's all burned in forever, but people tend to use the secure element solution because it's easier to buy them kind of with the CA, with the PKI accompanying them, in a way that you can go to mass production more easily and keep track of everything, in the factory, and get everything ready on the cloud, so that when that device is purchased and commissioned by the customer, it joins your cloud infrastructure and it's already validated as a valid unit of your product. I don't know, Nick and James, did you have any other thoughts on where a secure element is useful beyond just boot security? I mean, boot security is a very valid concern, but the trouble is, if you've got a separate chip, it's very easy. It's much easier to circumvent any boot security that's relying on inter-IC communication.
Absolutely, thanks, Ed.
I won't go on. Let's have another.
I'm conscious of the time where we've only got a minute or two left, so I should pick out some questions that Rajiv submitted ahead of the workshop. So one of them here is, we've got many production machines are actually pre-industry 4.0. We've got potentially very limited internet connectivity. They were put into the field before we had as many considerations around cybersecurity and IoT, and people are looking to extend and do more with those things. How can we go about managing the risk around those devices in the field? James, I think you had some thoughts on this.
Yeah, well, I did think that if you've got an old device which is running a very simple very simple connectivity, that can be effectively segregated on inside an edge gateway effectively. So that the edge gateway will then mediate any communication that has with the network at large and hopefully secure that. So
Absolutely.
That's obsolete.
Yeah, and that's a model and a sort of an architecture that we've seen and helped several customers deploy. In that setting, I've got this old control system. I want to connect it to IoT and get the insights and the benefits that go with that, but I don't want to replace all of these sensors and units that are in the field. So using a gateway to bridge those two worlds is a common approach that we see.
That kind of ties in a little bit with the question from Akim as well. I'm not personally familiar with IEC 62443 intimately, but for most operational technology and SCADA systems and things like that, then there's a lot more kind of segregation and firewalling approach than kind of implementing countermeasures inside of the device or the software and firmware itself, particularly where they're not greenfield implementations.
Absolutely. Thanks, Nick. Right, so we are at the end of our time today. So I'd just like to thank you all for your participation and some great questions. Hope you found it useful. As has been said on the chat, recording of the whole of the workshops will be available later on today. I believe anyone who registered should receive an email with a link to that. If you don't get that, please feel free to chase that up. And if you have any follow-on questions, I'm sure the team would love to engage with you. So please don't hesitate to get in touch. There should be contact details for myself and Alex Sangma on the on some of the materials you've had here. So please don't hesitate to reach out. And last but not least, thank you to James, Ed, and Nick for your time and your insights today. Very much appreciated.
Well, thanks everyone for coming.
Thank you.
Cheers, guys.
Thank you all. Take care.